All right, let's get right into it. If you've ever stared down an AC electronics problem, you know it can feel like trying to nail jello to a wall. I mean, everything is constantly changing, always moving. But what if I told you there's this incredibly clever mathematical trick that takes all that dynamic, complicated mess and turns it into a simple, static picture? Well, today we are unlocking that very shortcut, the phasor. So let's start with the big question. Why is this so tough in the first place? Why do alternating current circuits give students, and let's be honest, even experienced engineers such a headache?
Visit youtube.com/avidsystem and don't forget to subscribe.
Well, it all comes down to the nature of AC itself. In these circuits, the voltage and the current aren't just steady numbers. Nope, they're sinusoidal waves, just endlessly going up and down, up and down. They've got a peak, a frequency, and a lot of the time, they're not even in sync with each other. And that's where the real struggle begins, when you try to do math with these constantly shifting waves. I mean, if you try to tackle this head-on, it is just a pain. If you want to add two voltages together, you can't just add their peak values. You have to bust out these clunky, cumbersome, trigonometric identities to combine the full wave equations. It's slow, it's messy, and it is so easy to make a tiny mistake. It just feels wrong, like there has to be a better way. And that leads to this universal feeling. Seriously, anyone who has ever wrestled with those long equations has had this exact thought. It feels like you're using a sledgehammer to crack a nut. And the good news is, you are, because a much, much better tool is out there. So let's meet the hero of our story. We're going to take this messy, time-varying problem and solve it by taking what's basically a vector snapshot. It's time to introduce the phasor. Okay, so this is the formal definition. Now, don't let the term complex numbers scare you off. All it really is a way to describe a point on a 2D map. It has two key pieces of info, a magnitude, that's just its distance from the center, and an angle, which is its direction. And believe it or not, those two little things are all we need to capture the entire essence of our sine wave. So here's the best way to think about it. Picture an arrow, a vector, spinning around a point, kind of like the hand of a clock. As it spins, the height of its tip traces out a perfect sine wave. A phasor is what you get if you hit pause on that rotation right at the very beginning, at time equals 0. It's a snapshot that tells you everything important about that wave without you having to watch it spin around forever. And this is it. This is the big aha moment. We are literally taking a complex, moving wave and turning it into a simple, static arrow. All that messy trigonometry, all that constant change, it's about to get replaced by the simple geometry of arrows. So how does this magic trick actually work? How do we get from a wave to a vector? Let's roll up our sleeves and break down the anatomy of a phasor. The process is just beautifully simple. It's 2 steps. First, you take the peak value of the wave, its amplitude, and that becomes the length or the magnitude of your arrow. So a bigger wave is just a longer arrow. Simple. Second, you look at where the wave starts in its cycle. That's its phase. This becomes the direction your arrow is pointing. That's it. It's a direct one-to-one translation. And just look at the result of that translation. On the left, you've got the full clunky equation in the time domain. It's got time, frequency, phase, amplitude, the whole shebang. But on the right, in the phasor domain, look how clean and simple that is. Just the amplitude, Vm, at an angle of phi. We've thrown out all the complicated stuff, like the time and frequency, because in any given circuit, they're the same for all the signals anyway. And the place where we work with these new arrows is called a phasor diagram. Think of it as just a 2D plane with a horizontal axis and a vertical axis. This is our new playground, our canvas, where we can draw these vectors, see how long they are, what angle they're at, and do all our math. Okay, so the theory is cool, but what's the payoff? What can we actually do with this? Let's see these phasors in action and watch how this simple idea gets us some seriously powerful results. So remember that horrible trigonometry problem adding 2 waves? Watch this. With phasors, step 1, turn each wave into its arrow. Step 2, just like you did in physics class, stick the tail of the second arrow onto the tip of the first one. Step 3, draw a brand new arrow from where you started to where you ended up. That new arrow, that's your answer. And if you need it back in waveform, you just do the translation in reverse. It's that easy. We just replaced a page of trig with a simple drawing. So this is the really crucial point. This isn't just a neat little trick. It is a fundamental, absolute game changer for analyzing circuits. This is the engineer's shortcut. And here's why it's such a big deal. First, all that complex calculus you had to do for components like inductors and capacitors? Gone. It becomes simple algebra. Analyzing entire circuits just gets way, way easier. Adding or subtracting signals is now totally intuitive. You're just drawing arrows. And maybe best of all, you get a clear visual picture of what's happening in the circuit. You can actually see the relationships between voltages and currents at a single glance. When you boil it all down, it comes back to this one idea. Phasors are the essential tool that lets us take a problem where everything is constantly moving and turn it into a static, frozen picture that we can solve with pretty basic math. It's a huge shift in perspective that makes really hard problems easy. And that kind of leaves us with a final thought, doesn't it? The phasor is such a brilliant example of how just reframing a problem can make it solvable. It really makes you wonder, what other tough problems out there, in science, in engineering, maybe even in our own lives, are just waiting for the right change in perspective to suddenly become simple?
Thanks for watching.